Let's start as we always do with how computer memory works. So here's a simplified picture. Over on the left, the CPU, on the right, some memory. And we want to fetch. The CPU wants the contents of memory. To get it, it puts an address on the address bus. It asserts that it wants to read. The memory then goes and looks up that address and gets the contents, puts the result on a data bus. The CPU latches that, and everyone's happy, and then a read is complete. If it wanted to write, the CPU would put an address on the address bus, put data on the data bus, and assert the write line. In reality, this is much more complicated, right? This is we don't want to move memory byte by byte or even 16 bytes like we see here. We need to move memory in terms of pages. In addition, our little memory controller has to worry about how things are stored internally in flash, and so it's not this nice, perfectly linear system, right? Everything is going to be more complicated as we dive into it, but this simplified picture will serve us pretty well. We're thinking about the world in terms of a flat memory model, what we would call a flat memory model. There's a series of addresses, there's a byte at every address, and that's how we think of the world. And that model can work pretty well if you're only running one process and you're in a pretty secure environment, okay? So for like your Apple II, it's fine. But as you start to add memory and begin to get more complicated, pretty soon you hit some limitations. For example, here's the Commodore 64, a computer that touts 64K of memory. Huge amount, giant amount, right? It's 1980s, that's a ridiculous amount of memory. But think about this for a minute. Computers store their operating system, such as it was, in ROM. Now, if I only have a 64 kilobyte address space, and I want all of that to be RAM, where does the ROM go? It has to go somewhere in that address space. And the answer is bank switching. I take a chunk of addresses and I can switch in ROM so that then when I read from them, I'm reading from ROM, and then I can switch out the ROM so that when I read from them, now I'm reading from the RAM. And that's in fact how the Commodore 64 worked. Typically there's a memory address or a special register that lets you control which banks are switched in and which ones aren't. And thinking about memory this way means that sometimes an address means one thing and sometimes it means another, and in reality it's becoming a little fuzzy, and you start to think of memory maybe the way you think of other things on a computer, as a virtual thing, right? It's virtual. Maybe I should think of addresses as if they're virtual addresses, because why not? Once you go down this road, pretty soon you're going to find yourself thinking of memory in this way, in terms of virtual addresses, and in fact it's going to be 1966 when this happens to you. In 1966, the paper you see over there on the right was published, Program Addressing and Structure in a Time-Sharing Environment, and at the bottom of the page you see all these little arrows going around. That's because we have now got virtual paging and addressing, and pretty soon you are starting to build systems where you need a computer to manage the memory for your computer. And the computer you're using to manage the memory for your computer we call a memory management unit. The job of the MMU, which is another little computer inside your computer, is to translate what we would think of as virtual addresses into physical addresses. So you give me a virtual address and you say, I want to read from memory location 50. And the MMU says, okay, that's really going to be stored at this weird location, and I'm going to go fetch that weird location that you won't know about and give you back the result. And I'm going to do this in a way that makes it look consistent to you. Great. And there are big advantages for this. Memory protection. Every process can have its own virtual view of the world. Okay? Think about process isolation. You run a set of processes on a computer at the same time someone else is running a set of processes on a computer, and you each have memory and access to files and all this stuff, but it's partitioned so that you don't interfere with each other. And the same thing is the case here, right? We can isolate processes so that they can even have their own, what looks to them like a flat memory space that belongs entirely to them. So memory protection is a big deal. Memory fragmentation is a big deal. So think about this for a moment. When I have a flat memory model, I have to sort of say where I'm going to store each thing. And if something gets bigger, I'm out of luck. I have to find a way to move it somewhere where there's a contiguous spot of memory that has more room for it. And if I can't find that, then I can't do it. And so the more things I have in memory, the more broken up it is, and the less flexibility I have. Another thing that I can do is use address translation. And the nice thing about that is different processes can use the same virtual address space. So maybe I say, I'm putting this stuff for your process at this location, this set of addresses. And in fact, that could be the same for all processes. Okay? And I could do things like map a shared library into memory and then virtually map it across all processes, so it shows up in all of their memory at that address. Caching. One of the things that you get from this kind of approach is caching, and we'll talk about a little bit about that later on. But you've got several levels of cache in a modern processor. Some of it on the die, some of it shared among cores, and it just provides faster access. Large memory. One of the things you can do with the memory management unit is access memory that is larger than the processor's address space. We talked about bank switching with the Commodore 64. Same kind of principle here. Today, you're probably not going to have that, right? You're not going to have the full massive space of your computer taken up with DRAM. You could, but man, it's expensive to do that, and so you're probably not going to do that. So the virtual space is going to be much larger than the true amount of memory you have. But it doesn't have to be. The opposite can be true because of virtualization. And error detection. You can catch some bugs early in your program thanks to memory protection. If I reach out for an address and that address doesn't exist yet in my virtual world, I can generate an exception. In a flat memory model, when I reach for an address, it's there, right? All the addresses are just there. But in the virtual world, I can catch that and trigger an exception. So the way this typically works is you divide memory into pages, and you keep track of those pages in a page table. This seems like something that's going to be complicated. It's going to require some work, and in fact, we'll see it requires a lot of work. And so because the translation of a virtual address to a physical address is somewhat complex, we're actually going to have a cache for that translation called a translation look-aside buffer. All right. How do page tables work on the x86? Well, conversion of an address, a virtual address, to a physical address is done through 4 levels of page table lookups. Pages are 4K. They can be other sizes as well, but for our purposes, they're always going to be 4K. Right? I think there are 3 different types of page sizes you can have on the x86. It's going to be 4K. Just assume it's 4K. 4K is 12 bits, right? You can figure that out in your head, right? You know 10 bits is 1024, and so therefore you add 2 more bits, you multiply it by 4, and you get 4096. So, the bottom 12 bits of a 48-bit address, these bits down here, are the offset into a particular page. The remaining 36 bits of our 48-bit address space are broken up into chunks of 9 bits each. So here are 9, here are 9, here are 9, and here are 9. Okay? And each group corresponds to a level of the page tables. You may be thinking to yourself, 64-bit x86 and you're saying 48 bits? You're right. I mean, that's a difference there. It could also be 40 bits. So bear with me. We don't want to get too deep into the minutia of how the x86-64 works. If you want to know all that stuff, take the reverse engineering class. The register CR3 holds the physical address of the level 1 page table. And if you happen to be running in the kernel, you can access it. And if you're not running in the kernel, you cannot. You might write some code to try that and see what happens. You'll get an exception. But that's what kicks the process off. CR3 tells you where the level 1 page table is. All right, how do all these work together? Well, here's how they work. You can see down here, CR3 points to the start of the level 1 page table. And the page table is 4 kilobits. Okay? And so there's the level 1 page table. And then here's our level 1 page table index of 9 bits. That points to an 8-byte address somewhere in here. So I said it took 12 bits to cover 4096 bytes, and now I've got 9 bits over here. That's because these 9 bits point to an 8-byte offset, right? They point to a chunk of 8 bytes. 8 bytes, that would be 3 bits. We take the 12 bits, we subtract the 3 bits, we wind up with 9 bits. So this divides the world up into, tells you which of the 8-byte chunks you're pointing to. So it points to that one. So the processor goes to CR3, gets this location, gets the level 1 index, goes here, pulls this address out, and that points to the level 2 page table, or a level 2 page table, okay? And that level 2 page table is also 4K, and the level 2 index points to an address somewhere in it, and that points to the level 3 page table, or a level 3 page table, right? There is one level 1 page table. But you see, all of these could point to different level 2 page tables, and all of these could point to different level 3 page tables. And then, of course, we're going to use the level 3 page index into there, get an 8-byte address. That will point to the level 4 page table. We'll use the index into that. We'll get this address. Where does this point? Well, that finally actually points to a page in physical memory. So now we're pointing to a 4K page in physical memory somewhere. Now, all of these are, of course, stored in physical memory. This is a real physical memory address. It's not a virtual address. And each of these are real addresses. They're not virtual. Okay? That's how we can interpret this thing at the top, which is virtual. So now we're pointing to a chunk of 4 kilobytes, and that offset comes into play. It tells us specifically which byte, right? We don't need 9 bits. That's not enough to point to a specific byte in here. We need 12 bits to point to a particular byte. And now that's how we get from this thing at the top, which is a virtual address, to this location over here, which is an actual physical address. Super simple, right? If you're thinking, this seems like something that would take the processor some time, right? It has to look at a register, that's fast, then go and look in actual physical memory, get a location, go to other physical memory, get a location, go to more and so on. Yeah, it takes time. These things are typically going to be in your cache. Even so, it's still going to take time to decode these addresses. So what you do is you create a translation look-aside buffer, which speeds up the process, right? If this virtual address is already in the TLB, then you can just go ahead and grab it. Okay, and typically you just want the page address. You don't need all these last bits. You just want this thing that points to the actual physical page, and that's what you'll get. In addition, I mentioned cache before. The translation look-aside buffer is a kind of cache, but before you get to the DRAM, you've got other layers of cache, right? The CPUs talk to their own personal L1 caches that are fast but small. Their L2 caches, which are bigger and still pretty fast. The L3 cache, which is shared among the cores. And think about this for a minute. If CPU 0 and CPU 1, which are doing work at the same time, need to access the cache, we have to have some way of doing arbitration so that we don't give out inconsistent results. And finally, if there's a cache miss here, you have to go all the way out to the DRAM to get it. And there's a ton of things, if you really want to get into this: sequential consistency, cache coherence, lots of things that you need to think about in this world. And pretty soon, between address decoding and cache management and all of this, things begin to get very, very complicated. How complicated? Well, it turns out that the x86 memory management unit is Turing complete. Now, I want you to stop for a minute and think about what that means. And you can sort of see this little game of life being played over on the right side of the screen. That's being done without executing any x86 instructions. It's being played entirely through page faults in the MMU. It's Turing complete. And you can imagine that maybe that's scary. You can head over to that page. The code's open source and it's available. And there's a paper on it. It's pretty neat stuff. But really, we've backed our way into having to have a full Turing-complete computer just to manage the memory for our main computer. Okay. So here is a simplified view of what a Linux process looks like. We saw a piece of this when we saw the stack last time, but this is maybe a little bit different view, and I've laid it out horizontally here. And we have the low addresses, right? Here's address 0 over here. And we don't typically use address 0 because for a lot of languages, address 0 is the null pointer. And then over here on the far side, we have the address that's all F's in hex. That's the highest possible 64-bit address. Now, the entire 64-bit address space is not actually available to you. Typically, you have 48 bits of address space available to you, but don't worry too much about that. Your process usually, unless you have address space layout randomization enabled, your process will often want to load somewhere around here. And you may wonder, why is that address there? All those 5s would usually indicate that you're in a movie, right? If your phone number is 555 something, you're probably in a movie. Well, in this case, this is just there because that's about 1/3 of the total 48 bits that are available. It's arbitrary, but that's where we tend to start things. And then you have your program laid out. So you may have something like the PLT, which is the program linkage table. .text is your actual executable stuff. .data is read-only data. BSS is the I forget what that BSS stands for. It's something segment something. Sorry. Anyway, it's more data. Here's your heap, which is growing upward. Here's your stack at high memory, which is growing downward. We don't want those two to meet, so we can put a trap or a canary between them, or we can put other stuff like libraries in here and detect when they encounter each other. Lots of ways to lay this out. And there you go. That's your basic layout for your process. So, memory request. I convert a virtual address used by the processor to a physical address used by the actual memory subsystem using page tables. I communicate to the cache controller, which their cascade of things happens, and eventually I get a result back. And if a cache hit happens, it's fast, right? I get the result back from the cache quickly. A miss all the way out to DRAM is slow. I'm gonna notice that it's suddenly very, very slow. Okay, enough about memory. Now you've got your memory primer in your brain. Let's talk about out of order execution. The processor is always trying to do work, and it's always trying to fill a pipeline of instructions, and some of those instructions are simple and fast, and some are slow, and they take a long time to wade through. For example, I'm going to increment a value in a register, fast. I'm going to store a register in memory, that's slower. I need to fetch something from memory and add it to something else that's in memory, that's going to be really slow. So what I'd like to do is execute all the fast instructions while I'm waiting for the slow instructions to get done, right? So you're working on a project for school, and you have to do 3 or 4 things. You want to do the stuff that's easy and quick to do and get it out of the way, and then, do the other stuff. Or if you're working in a team, you want to give one person this long piece to manage while everybody else can get the other stuff done while that's being worked on. Processor tries to do the same thing. So if an instruction is going to take a long time, it wants to do other stuff in parallel with it. And so what it might do is keep a pipeline of instructions, do a little bit of data flow analysis, and then execute the instructions it can execute while waiting for the previous ones to get done. So it might do things out of order. If something goes wrong in the pipeline, that's okay. We just throw the rest of the work away and start over. It's not like we've done anything wrong. Modern x86 x86 processors can process about 200 instructions at a time. So you can be doing an instruction and at the same time doing one 200 instructions further along in the pipeline. So there can be a lot of out of order for those processors. The page table system has permission bits. So once the virtual address is converted to a physical address, the processor can check whether you have permission to access that memory. And it can generate an exception if you don't. And this gives you processor level security, which is great, right? That's better than software level security. The processor itself is going to stop you. Now, because this is super duper secure, the entire kernel and its working memory is mapped into the address space of every process because it's much more efficient, right? Think about what has to happen. If I have to change my context to execute the kernel, that takes time. I got to reload a whole bunch of addresses, a whole bunch of stuff's going to happen. But if it's mapped into the address space of the process, I don't need to recompute a bunch of addresses and do a bunch of other work. It's just there. And it's okay because it's protected by the memory subsystem. I can't read from it or write to it because the processor won't let me because I don't have permissions in the page table. Problem solved. Or is it? So let's think for a minute and let's do the following sort of mental exercise. I flush the cache. So everything in the cache has been flushed out to memory. I perform some action then. While that action is going on, I attempt to read from a memory location that I may or may not have access to. So I do some long instruction. It's going to take a long time to get done. And then I follow that by an instruction that reads from an address that maybe I may or may not have access to. I use the value that I read to then trigger several other reads. Okay? Now, meanwhile, the processor finishes with that instruction and it gets to the next one, and at that point it decides you shouldn't have read access. Now, why is it just deciding it now? Well, the previous instruction, the one it's working on, could have changed my permission context. And so really, it didn't know. Maybe I'd be able to do that. And so let's go ahead and do it. Because if it turns out I don't have permission, it can throw that work away. And there's no harm, no foul. But if I do end up with permission, it's already done that work. Right? So you say, I want the file on this person. And so there's two people there. One of them says, I'll check to see if he has permission. You go get the file. Someone goes off and gets the file. They come back. They've got the file in their hand. He says, I checked. He doesn't have permission. Fine. You don't give the file to him. You go and put it back in the cabinet. Well, okay. That all sounds pretty good. Seems like it would work just fine. But the memory locations we read from in that process are now in the cache. And so if we read from them again, they're going to be fast. And we can detect that they're fast, which means they were loaded. And if we load them based on the result we shouldn't have been able to see, we can infer the result we shouldn't have been able to see by what got loaded. And in fact, that's a well-known exploit called meltdown. And there's a CVE for it. KPTI is the mitigation for it. You can go read about that if you like. But this allows you to read from kernel memory while you're just operating in normal user space. And that's bad, right? That breaks one of the important security models of the processor. And we're able to do it because there's a side channel. We couldn't directly get the memory, but the effect of our having gotten it, the effect of the processor doing that work in anticipation lives on. There's a side channel that can reveal to us that what that result was, even though we can't get it directly. So meltdown has a CVE, and there's an associated CWE, CB200, exposure of sensitive information to an unauthorized actor. That's another example of a side channel. All right. Whew. There was homework, and the homework was to go and revisit your threat analysis using Stride. Hopefully that was helpful and interesting and productive, and you maybe found some new threats or thought about the threats in a new way. Let's talk about some information security models. So here is our friend the CIA triad, which you're all familiar with, I hope. Some of you seem to be struggling a little bit with, at least in the past, I've had students that have sort of struggled with what some of these things mean. So let's go through them real quickly. Confidentiality is control over information to prevent unauthorized sharing. Okay, the key there is unauthorized sharing. I keep the confidential information, your grade, your social security number, etc. I keep that secure, and I don't share it unless the person I'm going to share it with is authorized to have it. Integrity, the data being used is authentic, accurate, and reliable. So I give you a result back, I tell you what your grade is, the grade is stored in the system. That grade is the correct grade, and it's not going to be tampered with or modified unless someone has the correct authority to do it and does it in a way that can preserve the integrity of the result. And availability. Systems must be functioning as they should and when they should, right? I want to log in and see my grade. Well, iLearn needs to be up, and when I click on the button, it needs to give me the result and show me my grade. We can expand the triad, and many people have. One of the things we didn't talk about is, well, what if availability and confidentiality, I mean, those two things, maybe they seem to be in a little bit of conflict there, right? Availability tells me I should be able to get to the system and get the information I need. Confidentiality says, yeah, but only if you're authorized. Well, that could get in the way of potentially of me getting some work done. And so there has to be a way for me to guarantee that I can get the information I need in some form to do my work. And if availability and confidentiality come into conflict, I need to consciously think about how to resolve that. And we call that utility. Right? The data I can get is useful for the purpose at hand. We'll think about that a little more when we get to privacy, but maybe I need to get access not necessarily to the confidential data, but to something computed from it so that I can do my work. In the same mold, we might think of integrity and availability, and if we think about the two of those, we might end up thinking about authenticity, right? the data that we have is from the correct source, right? I put your grade in. You didn't put your own grade in, because those are different things, okay? And so authenticity tries to capture that. Similar to the other point gets one. Confidentiality and integrity, possession. We want to maintain positive control over all the different assets to ensure that we can satisfy confidentiality and we can satisfy integrity. So now we have 6 things around our 3-pointed triangle. We've covered the sides and the corners, and that is the Parkerian hexad. It's another way to look at the attributes of information security systems, and it emphasizes some elements as distinct from others that we might have thought about as just part of that. And if you wanted to try to slice it up more, if you wanted to take utility and confidentiality, utility and integrity, and try to say, is there something between those that's a property? Yes, people have done that. There are a million different models. One of the reasons CIA is so nice is because it's simple and it covers so much ground. The Parkerian hexad is still pretty simple, and it covers, a lot of ground. There's a 4-step security model that's fairly common. You'll encounter that out in the world. Authentication answers the question, who are you, right? So you tell me that you're a user to iLearn, and so I say, well, prove it. Give me a password. Give me a 2-factor token. Okay, now I'm willing to believe you are who you say you are. Availability. Is the data accessible? Authorization. What are you allowed to do? Are you a student? Can you look at your grade? Can you look at your own grade or someone else's grade? Are you a TA? Are you the professor? Can you put a new grade in? And then authenticity. Is the data intact? And there can be ways to check that, right? There can be error correcting codes and other things that can help guarantee that the data is preserved correctly. And the nice thing about this is it gives a set of things to evaluate before you perform an action or before you grant access to information. Right? You can check to be sure that they're authorized, the data is available, they've been authenticated, and the data has been authenticated. And all of that's true, then I can grant you access. Hope that makes sense. All right, let's shift gears and go back to identifying threats. So we talked about, we did an ad hoc approach, and then I gave you a really quick introduction to Stride, and I said, go back and try to apply Stride and see what you get. And here's our threat modeling slide again. What are you building? What can go wrong? What should you do about the things that can go wrong? And have you done enough analysis? And let's go back to Stride. So here are the Stride pieces: spoofing, tampering, repudiation, information disclosure, denial of service, and escalation of privileges. And here's our quick definition slide, right? Spoofing an identity is pretending to be someone else. Tampering is just what it says, tampering with data. Repudiation, doing something and then being able to claim that you didn't, maybe modifying logs. Information disclosure, giving information to someone who shouldn't have it, or obtaining information, or obtaining access to information you shouldn't have. Denial of service, just what it says. And elevation of privilege, someone achieving privilege levels that they're not supposed to. It's still a very high level, right? It's better than, maybe it's better than nothing or the ad hoc approach, but it's still a fairly high level. So let's talk about each one a little bit more. Spoofing is pretending to be someone or something that you're not. Okay? And I mean that in the general sense, right? I said someone or something. I pretend to be a different user, or I pretend to be a program that should have access. Or I pretend to be the login prompt, right? Pretending to be the Windows authentication service is an example. You can pretend to be PKExec. Right? You could pretend to be the Windows login screen. If you do these things, if you're pretending to be one of these things, people may try to log in and they'll enter their username and their password, and then you can pass that along to the system to log them in, and also perhaps pass that along to a file you're keeping or a network connection you have open to store that. If you want to see an example of this, there's a fake login screen project on GitHub you can go and take a look at. In the old days when we had, sort of a text prompt for logins, you typically had to go and you were running a computer lab. You'd have to go and be sure that when people left, all the processes that were running on those machines, they were all killed off, because someone could easily leave behind a process to capture information from people who came along after them, and we didn't want that. You could create a Trojan executable in the user's path, such as replacing sudo. So when they say sudo, it comes back and says enter the administrator password or enter your password. They enter it, you capture it and store it, and then run the command on their behalf. Why not? I mean, that's fine. Create a sudo, stick it in someplace, point their path to it, and they'll never know. Are you running in a VM? Well, great. We can try different things in that case. We could tamper with environment variables, like we showed before with the exploit. All those sorts of things will let us spoof something, right? We give, instead of giving you the real character set conversion, we give you a malicious one that does something else. You can spoof your MAC address. You can spoof your IP address. It's harder, but you can do it. You can pretend to be a user you're not, and you could pretend you could walk into a building and be like, I'm supposed to be here. I got a clipboard. I've got I've got a thing on a lanyard. I'm obviously supposed to be here. Let me go back in here and verify that your phone system is working, right? Pretending to be someone that you're not. And so the question to ask yourself is, does any part of your system rely on authentication of users, or software, or servers, or data, or anything else? And you should think about the impact of that being spoofed. Tampering, right? Just modify anything you have access to. Change data in a file. That's the easiest one. Intercept and change data on the network. If you can, why not? Overwrite temporary files. The temp file system is great. There could be processes writing stuff in there, reading stuff from it. Go and look and see if you can read those files, or if you can write to those files, and see what happens when you do. Change permissions on things. Modify the user's path, right? Tamper with their path, and that can enable the stuff we just talked about. Change web parameters, right? You're using a web-based tool, and you see that it's producing these complicated looking URLs that have little strings in them. Go and mess with those. See if you can get someone else's data, right? Find hidden fields in a web page and change them. So pop open that developer tool in Firefox or Chrome and go and look at the stuff that's in it. Look at the stuff in post requests, etc., and see what's there. Spoof environment variables. And the question we have, the question to ask yourself is any part of your system modifiable by the user? And if so, what happens if the user modifies that outside the normal scope of operations? I'm storing stuff in a temp file. What if someone goes and messes with that temporary file? Can I detect it? Will I detect it? Should I maybe have a checksum over it so I can detect something funny has happened with it? Okay. Repudiate. That's easy. Deny everything. Right? That was not me. I don't know what happened. I wasn't there. I wasn't even in the room. This usually just goes around your code to reach what we would think of as the business level. Right? So someone ships you something, you never received it. Something bad happens. It wasn't you. You didn't click. You didn't use someone else's login, right? You know you didn't. Are there logs? Can you prove that I logged in as someone else? Oh, the logs got deleted? Tough, right? Tamper with the logs, spoof entries, then deny everything. Thing to ask yourself here is, do you keep logs? And if you do, are the logs secure? And what are the things that happen that you don't log that maybe you should be logging? Okay. There's applications here for things like distributed ledgers and those kinds of things. But the basic idea is think about what you need to know in the future. What do you need to log? What are you not logging that you might need to? And can people tamper with those logs? And if they did, could you detect it? Information disclosure. Basically, learn the hidden things, right? Go look at temporary files. There's lots of stuff in temp files. See what's in a process list. Sometimes what you'll see is there's one, you're running one application, but when you look at the process table, you'll see it spawning all these other little things that are running. That's interesting. Maybe there's something in there that can reveal some information, right? Maybe there's something in, when you look at the process table, maybe something's being passed as a command line argument to some of those other processes, right? So I'm a process, I run, I start up, and I get a key. And maybe I pass a chunk of that key to other processes that I'm running so they can talk to me, and I do that as a command line argument. Ooh, that's interesting, right? Because I can see that perhaps in the process listing. All right. Cause error messages, and then look at those error messages, because sometimes they can reveal some pretty interesting stuff. Trigger error reporting, and then check the logs. Logs are great. You can often find things in the logs. Allocate a chunk of memory, and then paw through it and see what you can find. And then find side channels, and check out URLs, and modify them, and read parameters, all these things, right? Go and see what you can learn about a process by any means necessary. The thing to ask yourself here when you're building a system is, what information must you keep secret, and how are you going to store that information? What's going to be your approach for security at rest? How do you move the information around from one part of your system to another, or to a remote system, or to storage, etc.? How do you secure the information in motion? Minimize the information you give out to unknown users, especially anything that might be security. Don't reveal, for example, which of the username or password is incorrect. Just deny a login, right? It used to be applications would say, you'd try an email address to log in, and it would say, there's no email. That email doesn't have an account. Or you try it, and it would say, the password is wrong, and you realize, oh, that person has an account on this system. That is information you're revealing to an adversary, and that's not good, right? Don't say anything. Just say, didn't work, man. Don't know why. Denial of service. The basic idea here is use up all the things you can use up. If you can use up all the resources in a system, other things can't get resources and they'll break. Fill the temp file system. Often it's a fixed file system that is separate from other parts of the file system. You can just fill it up. Fill the process table with a fork bomb. Bind up all the sockets. That will work. Allocate all the disk space. Find any particular finite resource and just use it up. You can diversify, and you can use most of many different resources, and that can cause problems. You can try to get deadlock or live lock, or you disconnect things or disable things, or even overwrite and brick things, right? All those are different ways of denying service. And what do you have to think about for your system? Well, what if you're in a situation where you're running out of resources? How does your code respond to that kind of event? Does it gracefully degrade? And maybe that's okay, right? You're out of memory, and so, you know what? I'm just going to print out of memory and terminate. I'm going to append, and that's going to be fine. Or maybe I am very critical control software that holds important state information about a system like the power grid or the fuel mix ratio in your car or something else, and I really don't want that to just not work. We can go back and think about the Ariane 5 rocket, which was launched. It had an error, an exception populated away to the top of the program, which terminated, and that's bad when your program that terminates is controlling a rocket in flight. Okay? Bad stuff. And then elevation of privilege, right? Be all you can be. So if you can, become root. If it's hard to become root, become an administrator, and they'll give you the root password. Mission accomplished. Get a job in management, right? Tell the IT guy to give you the root password. You're in, okay? Request additional privileges. So sometimes there'll be a process by which you can request to have additional privileges for your account. And sometimes people don't really look at that stuff. They're just like another account, click approve, 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 especially if lots of them come in. And so request additional privileges, you might get them. Join all the groups. Joining some groups gives you more privileges. That can be nice. Steal passwords, crack passwords, steal cryptographic keys, right? Find recovery keys. People write down or take pictures of the recovery keys and keep them around. Find those. Sometimes at some organizations you can take training, and once you've completed the training, they enable additional access for you. That's great, right? So you might take data center access training. It's offered. You just sign up for it and take it, and automatically the system grants you data center access once you complete the training. Congratulations, you can walk into the data center now. Okay? Create a spoofed application and then complain to IT about it not working. What do I mean here? I build a version of some application that just doesn't work, and I get the IT guys to try to help me with it, and I give them my computer, and they see that this thing is not working, and they maybe enter their passwords into it in order to try to get it to work, and I can steal lots of stuff using that. Stack smashing, heap smashing, bad inputs, stressing the system, taking a physical system and doing something like glitching the power can help you dump down the firmware. Tons and tons of stuff you can do. So the question to ask yourself is, does your application have privileges? Does it rely on privileges? Does it use something like role-based access? And how does it protect against different kinds of attacks? Stack smashing is moderately easy. You can build stack canaries into your program. It's a compiler option. But what about other stuff? You should think about all those things. Whew, that was a lot. So let's think about some of the boundaries. So your program has information flows and it has storage, undoubtedly. Programs just have these things. And it's critical that you identify these. You identify the information stores, temp files, databases, files stored in the system, and identify the information flows within the system. Information stores can be encrypted or clear, in memory, on disk, or remote. Right? Those are all different places you can store this stuff and different ways you can store it. If the information is encrypted, you need to explicitly identify who has to use the information in the clear, that is, not encrypted, and isolate those parts of the system. Typically, you don't take an encrypted store, decrypt it all in memory, and then just work with it. Typically, what you want to do is have a way to index into even the encrypted piece, pull out the smallest piece that you need to work with, decrypt that piece, and then work with it. That's a little more efficient way to do it. If someone compromises the system, maybe they get that piece, but they don't get the entire information stored. What if you have information stored in more than one place? That's important to think about. Think back to the beginning of the class. We talked about each processor having its own cache, its own L1 and L2 cache, and there being a shared L3. Well, what if you wind up with two different L1 caches that have a value for memory at a particular address that's different? Now I have a processor that's working, doing one thing, and it sees that memory contains, let's say, 40, but the other sees that memory contains 60, and that can break everything. So I need my cache to be coherent. Likewise, if you're taking information off of disk, putting it in memory, passing it somewhere else, you need to think about who owns the copy and which one is the real copy. If you've ever written any code in Rust, Rust forces you to confront this and sort of beats you over the head with it. Think about when information is copied, when it passes across the network and between subsystems, or it goes to another form. Right? I take stuff in memory and I serialize it, out into JSON or to some other format, XML. Each of those is an information flow, and you have to think about the endpoints and what the security is at each of those endpoints and in between. Am I just streaming open XML data between endpoints, or am I streaming it over an SSL channel or something else, right? What's the transport mechanism and what should that be? This gets us to the notion of a sterile field. So here we see an operating theater, and we see an infection control mechanism called the sterile field. There's a plane here, and the plane is the bed where the patient resides. And when you're in the sterile field, everything in there is sterile. Anything that's outside the field is not sterile. And so if something passes outside the field and it comes back in, it's contaminated it. So the field has to be constantly monitored to protect it. And this is a good example of a trust boundary. A trust boundary is a distinct boundary within the system so that all the enclosed subsystems, and that can include the data that's in them, have equal trust. And the basic idea is it's a sterile field for your system, for your data, for your computation. So whenever data or control crosses a trust boundary, you need to take some action to assure that the trust relationship that you think you're maintaining is not broken, right? Someone carries something out of the sterile field and then they want to bring it back. Maybe you have to stop them and say, you know what? No, you can't do that. That went outside. I can't trust it anymore. Or maybe they bring it to you and it's in a sterile container and you say, yeah, that container is sealed. I can verify the seal. That's okay to come in, right? This data that you're bringing in, it's from a trusted source and I trust it. It can come inside without violating my trust boundary. But you have to think about that. And there's lots of stuff that goes on here, right? Someone enters a query into your web application. One of the things you might do is go and clean up that string so that if someone's trying to trick you with a SQL injection attack or a PHP injection attack or something else along those lines, you sanitize the string so that now it's safe to be inside the trust boundary. Identify trust boundaries in your system and identify them on the system diagram. So here we see a system diagram. In this case, it's for a vehicle. And we can see that over here, we have the battery and the battery management system, and it's got its own little trust boundary around it, but it can talk to the rest of the powertrain, the anti-lock brakes, and so on. And all of this lives inside this red trust boundary, including the charger interface and the OBD2 port, the onboard diagnostics port. But once information flows across the diagnostics port, it's out here in the amber trust boundary. So there could be maintenance, there could be the human-machine interface, there could be the infotainment system, your stereo or the monitors or whatever you have, and your mobile device, right? These are all out here in this outer boundary, okay? And should information from them just go straight into the powertrain? No, of course not, right? You have to control what passes through, for example, this gateway right here. What's allowed to pass through it? What's allowed to pass through this trust boundary? And what's allowed to pass through this trust boundary to the high voltage battery, etc. There's a good example put out on the web by Oracle, and there's a link to it in the slide, and that link will take you here to this trust model. And I'm not going to go through all of this, but you can see there's trust boundaries built in here, and then there's a discussion below it of what the trust boundaries are, what's included, and how access control is managed for those. And then they talk about external data flows. This is exactly what I'm talking about. Being able to capture this information can reveal a lot about where threats are and how your system is going to manage those threats. Okay, different components, right? Here's the Kubernetes orchestrator. Here's a database with MySQL. Out here is an external monitoring system, and here are people, right? People can be components of your system. We have to think about them as well, and where do they reside with respect to the trust boundary? The attack surface is a trust boundary. It's a special one. It's the set of all the points on the boundary of the system where an attacker can try to enter, or where they can cause an effect, or where they could potentially pull data or access it. Any place where an attacker can get to you or get to your system, that's part of the attack surface. And it's useful to think of it as anything that an attacker can get to. So if you're thinking about your car, right, this is anything they can get to. They can crawl into your car, they can get access to stuff. If they can open your car, they can get access to more stuff. If they can open your hood, they can really get access to stuff, etc. The attack surface is a trust boundary outside of which you really shouldn't trust anything, and everything should be verified before being accepted. You can enumerate the attack surface for your system, and you can mark that on the system diagram. Here is the attack surface for a vehicle, and you can see lots of things showing up here. Smartphone apps may have ways to get access to parts of your vehicle. Engine ECU, that's the electronic control unit. Basically, it's a computer that controls the engine or the transmission, steering and braking, so on. All of these are different pieces that someone might have access to. Over here, TPMS, I'll pick on it. That's the tire pressure measurement sensor. It's a wireless battery-powered transmitter inside your tire that reports the pressure inside the tire to the rest of the vehicle, so it can tell you if your tire is low. And those have to be paired with the vehicle so you don't pick up signals from someone else's TPMS. But there's software running on the TPMS side and on the receiver side. Is there something there that an unscrupulous person with a radio transmitter could do? Maybe. Let's talk about CAPEC. Stride's very simple, but it's very abstract. If you have more detail, it's going to tell me more about what specifically to look for, and maybe more about what specifically to do about a problem I find. So let's think about attacks and attack patterns. An attack is someone using one or more exploits to take advantage of the system and achieve some negative impact. We can think of an attack as part of the larger cyber attack life cycle that includes reconnaissance, right? Finding out what you've got, weaponizing stuff, delivering that stuff, exploiting it, gaining control, executing your mission, and then perhaps maintaining yourself so that you can do other missions later. An attack pattern is a description of common attributes and approaches used by adversaries. So it tells you, here's what they tend to do. And attack patterns can define, you can think of them as defining the challenges that an attacker has to overcome to gain control of your system. Okay? You can think of them like you could think of design patterns, right? A design pattern is a common pattern of how to solve a problem in code. An attack pattern is a common pattern of how to solve a problem in overcoming a system's defenses. MITRE maintains, it's always MITRE, they maintain a thing called the Common Attack Pattern Enumeration and Classification. And you could think of this maybe as like a souped up, very attacker-focused Stride. There's a list of common attacks, but whereas Stride is a list of properties, security properties. And you can click there and it'll take you there. And you can look at this in many different ways. So over on the right-hand side, we see looking at it by mechanisms of attack and looking at it by domains of attack. And you'll notice that sure enough, hardware is in there, communications, supply chains in there, and even physical security is in there. It's very comprehensive. Because again, we should be thinking about the entire system that contains your software, not just the software itself. All right. So there's many different ways to paw through it. So it's not like that top mechanisms of attack and that bottom domains of attack. They're not disjoint. They take you to the same information. They just get you there through a different path. This is one of many attack libraries which attempts to catalog attacker methods. The OWASP Top 10 is another example of this. And let's pop over to CAPEC and take a look at it. And so many different ways to look at it, and to maybe even to map it to other things, like here's view by attack related patterns, view by OWASP related patterns. But let's go ahead and take a look at, let's say, domains of attack. And so if we click on this, it reloads and wind up here at domains of attack. And maybe you want to attack the software, so we'll expand that, or we can just click on it. And either way, you'll get this list. And here we go. And we can malicious logic insertion, modification during manufacture, and so on. So there you have it. And what about brute force? Let's click on that. Description of it, other related stuff, and then much more information than you could really ever want, including mapping to the CWEs, use of insufficiently random values that can enable brute forcing, inadequate encryption strength, weak password requirements. So those are things that can enable brute forcing, for example, passwords. Okay. Here's some stuff from the MITRE ATT&CK framework. Here's some stuff from the OWASP framework. There you go. And so that's one way to look at it. We can go back and maybe look at it by mechanism of attack. That brings us here. And so we have different stuff here, right? And we could look for maybe subverting access control. There's different ways of subverting access control, including physical theft, right? Physical theft is just what it says. I can steal the thing. An adversary gains physical access to a system through theft of the item. There you go. All right. Enough about that. And that's it.